thank you all for joining us this morning for the Winter Quarter Zurich Financial Services Distinguished Visitor Program on Climate Change. This program allows us to bring in distinguished scientists from around the world to teach a class and give public talks and work with students and faculty on a variety of issues in terms of related to the science of climate change. And we're delighted today to have Tom Swetnam from the University of Arizona. And Tom has the coolest title of any professor I've seen. I was at an event with him last night, and he has this tag on that says, Professor of Dendrochronology. And of course, I'm sure you're used to the fact of wearing that around in public, that nobody has any idea what that means. Or if they do, they make silly jokes like you being the Lord of the Tree Rings or things along these lines. I've heard that many times, I'm sure. But he's the Regents Professor and Director of the world's premier center for research and education in dendrochronology at the University of Arizona in their Laboratory of Tree Ring Research in the College of Science. He's a global leader in the study of wildfire and climate history, which ties into the efforts here in the CIRI program in terms of a Bren School-wide research effort in climate change and fire. And he is focused on forest ecosystems, including studies of some of the most spectacular forests on the planet, our coast redwoods and sequoias along the California coast, as well as the world's most extensive conifer forests in Siberia. And his work in recent years has focused especially on the effects of increasing trends in drought and temperatures, so it's particularly relevant to what's happening in California these days on the forests in the western US and central Siberia. He's teaching a class at the Bren School called Pyrogeography and Policy, Wildfire and People on a Warming Planet, which is started on Monday, but from what I understand, there's still potential if students want to participate in that. And it's 4 to 6 p.m., the next class being later on this afternoon. And today, Tom is going to talk about reaping the whirlwind wildfire climate change in the western U.S. Please welcome Tom.
Thank you, Steve, very much. Appreciate that. It's great, my honor and pleasure to be here. My sincere thanks to the Bren School and, of course, Zurich Financial for supporting this generous fellowship. And truly, it's always fun to come and talk to students, enthusiastic, energetic folks with experience and professional experience as well. So the class has been really, really interesting, and I look forward to the next few lectures. I also wanted to thank other folks, Naomi Take in particular, and Andrew Plantinga and Sarah Anderson made me feel very welcome here. And Sati Aremi, I really appreciate, thank you. There you are. Thank you also for your help in coming. And Casey as well, and BJ, folks have just made me feel welcome, and I do very much appreciate that. Well, okay, let me go to the slides here. And as you will note from this slide, this opening slide, I do have a rather ominous-sounding title here to the presentation, Reaping the Whirlwind, which is actually, if you've up on your King James Version of the Bible, you might recognize that phrase, and I'll say something more about that in a moment. Obviously, this topic is an important one to many folks around the western United States, the changes that we're seeing in forests and wildfire regimes. This is a striking image here from the Wallow Fire in Arizona. Let me see if I can get this little thing to turn off here. That little window. Yep, not sure how to turn that down. All right, well, didn't seem to run it forward here. Let's see. Okay, now maybe it'll work. Here we go. Okay. So in addition to wildfire scenes like the previous slide, scenes like this one have become increasingly frequent across the western United States. It's a rather iconic image, of course, of a pyrocumulus cloud rising over Los Angeles. And indeed, most of our big cities have had these amazing events, even within city perimeters or nearby, reflecting these really large wildfire events burning into urban interfaces and affecting our watersheds and ecosystems. This is just over my own hometown in Tucson, Arizona, a large wildfire that occurred in 2003. Impacting, again, people and ecosystems profoundly. That phrase, if it wasn't familiar to you, it's from King James Version, for they have sown the wind and they shall reap the whirlwind. So this is the, you probably might be more familiar with the phrase, you shall reap what you have sown. And it's a bit of a metaphor here in the sense of changes that humans have brought to our environment and to climate and to our ecosystems, unintentionally or willfully in some cases, and these changes coming back to haunt us, right? And in the sense of climate and the wind, of course, is really a key element here in wildfires, and increasingly so, and this is a bit of a theme of the talk today. This image actually is a fire whirl. It's one of the many different kinds of vortex behaviors that occur on wildfires from the scale of a few meters to even kilometer scales. And wind being a key factor there, as well as dry conditions. Those of you who were fortunate enough to attend Tim Egan's talk last night are familiar with his powerful writings, perhaps, and also this other book, National Book Award winner, his the Worst Hard Time book on the Dust Bowl. And this is an interesting analogy, if you will, of fire and the changes in our forests as well, in the sense that people have changed their environments, increasing their sensitivity and vulnerability to climate change. In the case of the Dust Bowl, the story of the movement of millions of people or thousands of people to West Texas and Oklahoma, and the plowing of millions of acres of ancient prairie and during the wetter period of the turn of the century, late 1800s, 1900, wet time period. And they were very successful with dryland farming there. And it was a boom time. And then markets collapsed in the late 1920s, and it turned dry. And many of these farmlands were left fallow, bare, with no cover. And then the drought and the winds came, and vast clouds of dust came and blew the soil away and blew the people away as well. The fabulous moving story. I recommend the book, Tim Egan's book as well. But it's this point of how we can increase the vulnerability of our landscapes through large-scale changes that we bring about. And the fire story has an analogy there. And the 1910 fires were this epical event that really galvanized the country. As Egan described it, utilized by Pinchot and Roosevelt to firmly establish the Forest Service and to establish that as the mission of the United States Forest Service, to put fires out. And Egan actually makes this connection. This is a quote from Ehlers Koch, who was one of the early forest rangers. He was one of the little GPs, the little Gifford Pinchots, who was sent out to the wilds from Yale and was on the 1910 fires. He was actually injured in the 1910 fires, survived them, and years later wrote a biography and also wrote some papers, a paper particularly questioning whether or not it was all a great mistake. This was, I believe, in the 1930s, and wildfires were popping up again in the West in the context of the drought, and he was questioning whether it was wise to be putting fires out. And this amazing quote here was that all this effort and expenditure of millions of dollars added up to anything to human good. Is it possible that it was all a ghastly mistake, like plowing up the good buffalo grass of the dry prairies? He had actually made that connection himself about the mistake, perhaps, of totally excluding wildfire from our landscape. So the problem there in many of these systems has been the changes in the fuels. It's not the case in all forest types or all vegetation types, but in some forests definitely is the case. And that connection was made long ago. And then drought and climate variability is also obviously a key factor. 1910 was extraordinarily hot and dry. It was the driest spring, actually. March to May temperature, this is the anomaly, temperature anomalies, the difference from the long term, it was the warmest spring until recently. Check this out. Look at the trend of spring temperatures is clearly ramping up since the 1980s, and we finally actually equaled the record and broke the record here in 2012 of warm springs. And this is really a critical month for wildfires, especially in our montane areas, because this causes this early snow melt, and then you have a longer drying period of the fuels into the summer months. I show this just to take note again, this ramping up. This is a major decadal scale phenomenon, and it's likely related to rising global temperatures. We can argue whether regional effects are distinguishable yet, but likely so. In any case, the record is clear. It's been warming across the continental United States, and wildfires have been ramping up during that time period. You all know this very well, living here in Santa Barbara in California today, an extreme drought, actually exceptional drought. This is February 25th drought monitor. You're in the bullseye here of the drought. Perhaps it's been moderated a little bit with the rain, but this is a longer term drought. It's actually going back over the Southwest and parts of California into the late 1990s. And indeed a hot drought, so lack of moisture, but also these rising temperatures compounding the problem. And obviously, everybody knows generally that when it's hot and dry, it burns, and there's a long-term history of this, not only from the 20th century records, but from paleo records. Okay, so here's the dendrochronology part, a little bit of dendrochronology. Tree rings, my specialty. We've been able to reconstruct long-term histories of forest fire activity around the West from remarkable trees, and of course the giant sequoia, the amazing giant sequoia. This is the grizzly giant in Yosemite. Virtually all of the old sequoias, every tree over 1,000 years or so old has got a fire scar on it, or multiple fire scars, these big blackened wounds at the bases. And actually, if you look closely inside these cavities, these deep fire cavities, there are many scars. There are many different dates of wounds. I'll show you an example here in a minute. But we had an opportunity in the 1990s to work in the sequoia groves. We worked in 6 different sequoia groves with large chainsaws. You'll be happy to know, only on stumps and logs from the previous logging. And we reconstructed really long histories, 3,000-year-long fire histories. This example, this is the display section that's in the parking lot in front of the General Sherman tree at Sequoia National Park, and we had the chance to surface that with belt sanders, put a nice smooth surface on it. We could see all of the whole section, which was unusual. We usually are taking smaller pieces with our saws. And this thing went back to about 200 BC. And the outer date was 1950. This tree was actually cut down by the Park Service because it was leaning over some cabins. And this tree had 85 different fire scar dates, 85 fire dates recorded in it. A very distinct scarring. This is actually an image of a fire-scarred ponderosa pine from Yosemite. And this is kind of classic example of fire scars on trees. The wounding it may be a little difficult to see, but there are lesions, there are black lines that come into individual rings, and we can see them under a microscope and date them to the year. And there's many, in this case, multiple fires separated by years to decades. There's one, there's the last one, 1896. And this is the kind of classic pattern we see in pine, ponderosa pine, Jeffrey pine dominated forests across the western U.S. generally, is this long fire exclusion period at the end. 100 years, 50 to 100 years of anomalously long interval since the previous fire. And this is the Smokey bear effect, if you will. Fire suppression having kept out these frequent surface fires that have burned in those kinds of forests. The sequoias are unique in that, we have thousands of years of record. Most of our pine records are 100 to 300 to 400 years long. But in sequoias, we got several thousand years of replicated record. Here I'm showing the last 2,000 years. And in this case, we were able to compare our fire scars from giant sequoias in red here This is a fire frequency. That's a measure of fire frequency. That's from the sequoias in red. And then the black dashed line here is actually from charcoal, from counts of numbers of charcoal particles in core, sediment cores. My colleague Scott Anderson from Northern Arizona University cored a number of the same groves, sequoia groves, where we had fire scars, and then using radiocarbon dating and counting the abundance of charcoal, he was able to develop long histories from charcoal, and then we compare those with the sequoia record, and you can see a pretty decent match for these kinds of data. It's actually pretty darn good. The key thing with the sequoia record, one of the key points, is that fire frequencies were remarkably high in the medieval period, from about 900 AD to around 1300 AD. Small areas, the size of this campus, basically the giant forest, we were finding fires burning over the majority of that grove about every 15 or 20 years. And in some places, even more frequent than that, and time periods, very frequent fires. And it drops off, the frequency drops off after about 1300 with some spikes. And then particularly notable is this period at the very end. After about 1850, there's very few fires recorded in the groves until the prescribed fire program was instituted in the 1970s and 1980s in the parks. And we've seen this kind of thing in other places around the West where we have sediment samples with charcoal and fire scar samples. Cases where we have one case in New Mexico with 7,000 years of fire history from charcoal, and the top 100 years of that 7,000 year period is virtually devoid of charcoal. And there's no other period like that in 7,000 years without fires occurring at the frequency they occurred before, and this is primarily due to livestock raising. Initially, this was due to the introduction of sheep and cattle and removal of fuels, which I'll say more about here in a moment, and then fire suppression. But on the climate connection, the medieval period is especially dry. This is a network, this is a gridded set of reconstructions from tree ring width chronologies. It's a very evenly spaced grid here because they took about 1,000 tree ring chronologies of drought-sensitive trees, and they calibrated them with nearby drought indices, nearby instrumental-based records of drought. So each of those grid points has an independent drought history reconstructed with tree rings. You can access this on the web and download these drought histories, the North American Drought Atlas. Well, the West, this combined set of grid points is composited here to look at the percent of drought area back to 800 AD to the present. And here's the scary thing. Here's the medieval drought, which shows up as really multi-century periods of extreme droughts. This actually shows up in other kinds of records too, such as Scott Stein's work on lake levels in the Sierra Nevada. He shows that these were some of the droughtiest periods as well, with low stands of lakes in the Sierras. Keep in mind too, right, so this is the period of settlement of the western United States. The Southern California, depending on surface water, was during this anomalously, well, generally wetter period. Far wetter in general. Imagine if we were to shift into a period like that, which we might be, all right? This is really bad news. Sorry. I mean, even if climate wasn't changing, which it is, and probably mostly caused by humans with increasing greenhouse gas, even if that wasn't happening, there's a problem. There's a problem living in the western US. And with the climate system can lock into decadal and multi-decadal scale droughts. And we're really not adapted to that. And we were fortunate, well, I may be unfortunate, to develop to settle here during wetter time periods, but it may not stay that way. And fires are part of the response of the system when it starts to get warmer. This is our larger network of tree ring sites over the western US. And we have composited now more than 800 sites. So all those little orange pins are where we have collections of fire-scarred trees, a dozen or 50 or more fire-scarred trees in a forest stand. And these are many different studies from many different researchers composited. And then we have the record from the tree ring width chronologies where we can map out the spatial patterns of drought with the ring width-based drought reconstructions. So the brown here is reflecting the 1748 drought, the extent of the 1748 drought, and the red dots that are showing up here are the sites that showed fire occurrences in those fire history sites. And the darker the red, the higher percentage of trees were scarred in those sites during that 1748. 1748 is an interesting year. It actually shows up only as a micro ring, a very tiny little lens of growth on some trees. It was so dry during that year that it actually reduced growth so much you only find it in some places on some trees. And the year before was extraordinarily wet. This is a common pattern, is wet, wet, dry is a real key to these highly synchronous fire years. Here's the chronology for all of those sites over the west, going back to 1600. And a couple of obvious characteristics, highly synchronous fire years across the western United States. There's 1748. Very large percentages of sites showing up in those years. Also, high synchrony of low fire occurrence years. And these are very well correlated with wet and dry patterns and lagging patterns, wet, wet, dry. So, for example, they also matches nicely with El Nino, southern oscillation patterns, and other kinds of climate histories and reconstructions. The other big thing is look at this, right? This is the deficit of burning. This 1910 right there in comparison. 1910 was the big year, but it shows up as fairly small compared to the pre-settlement era. These records are predominantly from pine-dominated forests, so it's not entirely reflective of all the western United States, but still general burning patterns. In these forests, especially that had these frequent fires, understory, frequent low-intensity fires, it's very obvious from all sorts of records, aerial photography, for example, that these stands have changed in this last century because of the lack of fire. So we see the last fire scars recorded in the 1890s, and we see a surge of trees coming in thereafter. You can see it in repeat photos on the ground and from the air and from age structures of trees. For example, this is the Santa Fe watershed. This is a aerial photo. This is a couple miles across. This upper watershed, the Santa Fe watershed, where Naomi has worked as well, showing this drastic change from 1935 to 2005. This slope right here is probably sort of a savanna grassland kind of a slope, a south-facing slope with grasses and trees, and then look how it looks 70 years later, closed in. Many, many more trees. This is a real problem in dry conditions, enabling fuels basically to carry fire into the canopy, and a threat to the watersheds because these have reservoirs, and the hydrological responses following fire, as you know, here in Southern California, can be pretty extreme. So there's a problem here, and again, I would want to say, and I will come back to this, is that this problem of changing forests is specific to some types, and the changes due to fire suppression is not the case in all types. Probably not the case so much in chaparral, but it is the case in many of these drier pine forests. And then on top of that, we have climate change. We do have warming temperatures, increasingly warm springs, and the increasing numbers of large fires. So this paper, Tony Westerling compiled large fires. So these are the fires over a couple of hundred hectares back to the 1970s, and comparing that with spring temperature is a pretty good correlation. The highest fire occurrence years corresponding with early springs. So snowmelt early, drying conditions. The most recent 20 years has 5 or 6 times more large fires than in the previous 20 years. And the fire season is about 2 months longer. So this 2-decade period has more than 2 months longer beginning of large fires early in the year, and then when fires are finally put out at the end of the year. We've seen these changes pretty strikingly. So the temperature changes are clearly a factor. And on top of that are the nonlinearities. That this is what really concerns me, and it's actually part of my presentation here to talk a bit about these nonlinearities and the extreme responses. If you look on the right here, temperature anomaly. So These are the temperatures over that period back to the 1970s, the anomalies relative to the long term, compared to the numbers of these large fires. And so these little dots representing fire years and how warm it was in the spring during those years. And notice it's a nonlinear relationship. So as temperature rises, the response of more large fires doesn't just kind of ramp up linearly. It has inflection points. It increasing more rapidly as the temperature rises. This stands to reason, actually, because fire is a spreading process. It's a spatial process. It probably would be increasing at these scales for lots of reasons. Another one, besides the spatial aspects and spreading aspects of fire, is that as temperature rises, the atmospheric demand for moisture increases nonlinearly. So this is some work by Park Williams, who is a graduate of here. Some of you know Park, looking at vapor pressure deficit, which is a measure of how much moisture is that the air is lacking, but could accommodate given the temperature. So as temperature rises, the atmosphere actually becomes more of a sponge. It's actually able to absorb moisture out of soils and fuels more rapidly, more effectively. So there's a nonlinear change in evaporative demand, if you will. So nonlinearities and changes should be expected. I mean, we actually should expect surprise. We shouldn't be surprised by surprises. And this is true of fire behaviors. And so I think we may be beginning to see some of these things, these kind of changes. We see it in the rates of spread of fires. We are now seeing fires of hundreds of thousands of hectares, multiple examples across the West, when before 1980, these were extremely rare, going back to 1910. And certain behaviors like this one, this is the Las Conchas Fire that burned near Los Alamos in 2011. You know how this thing is tilting like this? It's because it's being driven by wind, and it's also rotating. So this is a time-lapse sequence taken from Santa Fe, New Mexico by Michael Zeiler. He's taking a photograph about every 20 seconds from his Canon camera, 30 miles away. And note, these mountains here, these are about 10,000 foot tall mountains. You're looking at a huge plume that's a mile or two across, 30 or 40,000 feet tall. The smoke is actually going over Zeiler as he's taking this photograph. And notice the rotation. It's actually, you see it? If you can pick it out, it's actually rotating. There's rotation on it. And there's some other time-lapse images of this particular fire that from the other side, from the north side, and it's rotating the other way. So this one, it's a paired vortex. This side is rotating counterclockwise, and this side is rotating clockwise. It's what's called a horizontal roll vortex. It's kind of a scary thing, and because they move really fast, and as it's rotating, it's pulling wind into the front of the fire. All right, they're a little bit unpredictable, and they move very fast. This fire burned about 40,000 acres in about 8 hours, and at night, it was more plume-dominated at night, more vertical plume and then collapsing, but it blew down through pinyon juniper woodland. This is actually about a 400 or 500-year-old alligator juniper in was a very sparse pinyon juniper woodland that rarely or ever, if ever burned. There's very little evidence of stand replacing crown fires in these open, kind of sparse pinyon juniper woodlands. But this fire blew almost all the way down to the Rio Grande that night. It's extraordinary rates of spread. If there had been a human community in the way here, it would have really been a disaster. This landscape, as a number in the Southwest, they're reburning now. So this is near Los Alamos again, the Las Conchas area. Reburning areas that burned previously. There are 10,000 acre canopy holes. In fact, there's one that's got 30,000 acres of continuous total stand replacement. And there's basically no seed trees in there. And what's coming back are gamble oak resprouting from its roots. So this landscape, we think, is being converted probably to chaparral, to shrubland. This is perhaps the future of large parts of the Southwest is actually becoming like California, maybe, Southern California. So on the vortex and the connection with winds here, when I saw the Las Conchas fire burning, it reminded me of this old paper published in 1957 by Vince Schaefer. he was studying clouds and fire with Jack Dietrich, and they were up on the Mogollon Rim in central Arizona in 1956. And this fire ignited, this Dudley Lake fire ignited, and it blew across the Mogollon Rim in 6 or 8 hours with the wind driving it, and it was rotating. It was the first described horizontal roll vortex fire in the literature that I can find. And Schaefer made a connection, a somewhat loose connection, I would admit, with the jet stream. He was suggesting that the jet occasionally can basically low elevation members of the jet stream can come down and influence fires. And indeed, as the jet is directly overhead, this is not that unusual to have high wind speeds occasionally dipping down. If you remember Tim Egan last night talking about the extraordinary wind speeds in 1910. We don't really have, unfortunately, wind records from 1910 to know what was going on there with the jet, but it's possible that was related. What's going on with these HRVs, these horizontal roll vortices, has to do with wind shear, with really high speeds up high, and these plumes can reach near jet stream level, 30,000, even 40,000 feet. So very high wind speeds up high, and then slower wind speeds as you get down lower. So with the plume rising up, the top of the plume gets rolled over because it's being pushed faster than the bottom part. So you start getting a roll. And then with higher winds higher up, the horizontal roll splits, and you can get then the double vortex behavior. So there are different species of these things that have been observed. They're not well understood. There's sometimes single vortices, and there's double vortices, and different kinds of them that depend upon the terrain and the kind of wind that's blowing. But this is another example, the Wildfire, which is which is our biggest fire in Arizona to date. Again, what you can tell these by the plumes are laid down and being pushed versus the vertical plumes, like the one I showed you over LA. You've seen over LA. So those are more vertical, where you get plume-dominated fires. These are wind-driven fires. The effect of the jet stream is suggested, actually, in this case of the Wildfire. The winds, in fact, the jet was positioned just off the coast of California with very high wind speeds, and then looping up around through Arizona and New Mexico. So this is showing the directions and the wind speeds right during the days when the Wildfire was really exploding. And what you have here in the background is the Haynes Index, which is a fire index measuring dryness and also instability of the atmosphere. And 6s and 5s are really extreme. So there does seem to be a jet stream effect, at least partly. And this is really preliminary work I'm talking about here. We haven't fully analyzed this jet stream effects, but there's a number of interesting connections. And one of them I want to make really briefly here. It's again on the sort of preliminary science side of things. This is actually old science. This is the classic description of the jet stream and explanation of the patterns of the jet by Carl Gustav Rossby. Here's the man. So this actually, when was the last time a climatologist had his photo on the cover of Time magazine? 1956. It's really a great article, actually. And he's really one of the fathers, the godfathers of modern climatology. He worked out the equations, explanation of how the jet stream works and why you get this river of fast-moving air around the northern latitudes as a function of the gradient of temperatures between the equator and the pole. So this gradient plus the Coriolis effect creates a moving river of air. And he actually derives equations that would predict that the magnitude of the gradient will predict the speed of the jet stream, and the speed of the jet stream will predict how many waves there will be in the jet stream, how many oscillations. These are the so-called Rossby waves. So when you have a very, very steep gradient with lots of ice cover in the wintertime, and even maybe more persisting through the summer, then you have a steep gradient, then the jet is very zonal. It's very fast, and it's going to move zonally. And then when you have low ice cover and you have a low gradient, the jet slows down and it starts to meander like a river. A meandering river on a floodplain versus a river that's like shooting down a steep gradient. Fast and straight, slow and meandering. Okay, and so when this gets slow and meandering, then you get deep troughs, and you get very deep ridges, blocking patterns, and drying temperatures, and then cold outbreaks, polar vortex. This whole discussion has been part of the polar vortex discussion. Is this because of the decreasing gradient of temperatures from the pole to the equator? This is very hotly debated right now among climatologists as to whether or not we're detecting this, whether or not it's detectable, or whether or not there's natural variability that will ever prevent us from saying that the loss of the sea ice is causing these patterns. Suffice to say that at this point, this is a real phenomenon. Troughs and ridges, slow-moving jet streams, and heat waves and fire are connected. Whether there's a trend in them is yet to be determined. If it's connected to climate change is also to be determined, but it's an expectation, at least I would think is an expectation, that as the sea ice melts further, that northern latitudes warm up, that one might expect there to be more blocking patterns. This is the great heat wave that hit Moscow in 2010, and the bogs around Moscow were burning. I mean, actually, these swampy areas caught on fire, and it very, very bad time there with many people dying from smoke and heat. And then over here in Pakistan, downstream was flooding in Pakistan. Coldest temperatures in the spring recorded in parts of central Siberia, and then far eastern Siberia was burning. So these patterns happen. And it's not just the blocking. So imagine you have drying temperatures here, and the jet is moving. So these loops are they're moving. They're moving, west to east. So as this dries out for a couple weeks, then as this jet is moving across, you get winds. As the jet moves right across, and you get frontal systems and lightning. So there's a number of mechanisms in how these things can actually generate wildfires, be related to wildfires. This is the Wallow Fire, the footprint, the satellite image of the footprint of the Wallow Fire, and extreme run. This is a 10-mile long run right here. And you can zoom in on Google Earth, and I challenge you to find some living trees in there. This is about, I don't know, some thousands of acres of just crown fire patch in the red there. Extremely high severity fire during these wind-driven runs. So these linear features like this are quite distinctive. You can zoom in, and using historical imagery in Google Earth, you can see these straight edges going up and down hill slopes. They're very distinctive. This is 1967 fire. In 1967, still quite evident. A lot of these have these interesting tree streets, these strips of unburned trees out in the middle and on the edges, which we don't really know how those are created, but they're a feature of these wind-driven vortex fires. So I took the atlases, the fire atlases from the Southwest, going back to the 1970s. So this is the perimeters of areas burned, and I used historical imagery, and I identified as many of these obvious wind-driven fires as I could, and I came up with 161, so a pretty small minority of the total, but 161 clearly obvious wind-driven fires, and I measured their lengths and their directions, and this is what I get is they're very consistently southwest to northeast, which is the kind of classic jet pattern during the spring and early summer months. And notice that this is a log scale, so that's 10 miles length. So these are the run lengths along this axis. So the fires that exceeded 10 miles long, these runs that are exceeding 10 miles long, are pretty consistently the recent decades, but also a few from the droughts of the 1950s, those blue ones there. And this is the trends in numbers of those runs and their average lengths, so by decade. So this is the mean length of these wind-driven runs by decades, and then the bars are the numbers of these runs, these wind-driven fires by decades. Before 1970, I'm not so sure about these data here. So the trend is really, I would have confidence that this trend right here is an incomplete decade. So these things are increasing, which makes sense, I think, given the changes in temperature and the changes in fuels. So changes in fuels. I want to be sure to leave you some time to interact here, a little bit of questions. What do we do about this? Well, there are some solutions. It's very place and time specific. This kind of thing, mechanical treatment or prescribed fire, is appropriate only in some ecosystems. I think it is appropriate in many of our pine-dominated ecosystems, and especially in wildland-urban interface areas and really valuable habitats and watersheds that we need to mitigate the risk. And you can mitigate the risk. There are compiled meta-analyses and compiled studies now to show that, in general, these treatments can be effective. They're not always effective, but in general, the pattern is that they can be in the right circumstances. This was actually, let me go back, this is the case of the wildfire came over the rim here. They had treated this area right here, so it was actually a backing down the slope, which is good. But they were able to put handline and slurry drops in here, and they saved this wild-land-urban interface neighborhood. So that's just the anecdotal example. But again, there are some composited analyses of many different cases that generally show that it can be effective, but not always, especially when you've got wind. And especially in the types that you live in, chaparral, with the fuels that you have here, and the close proximity that you have to your homes. I think Carla sent this to me some time ago, and I think you said when you sent it, I'm not sure if this is photoshopped or not, because it's got all of the elements in there, There's fire, there's people, there's planes. Cool image, anyway. But yeah, this is the problem. People in really flammable landscapes where fuel treatments probably not ecologically justified because these types burn catastrophically, and they always have burned catastrophically. And wind blows the embers, so you have these maelstroms of swarms of embers blowing, and even if you put in a really big fire break, that may not be effective during a Santa Ana wind or a sundowner, right? So the fuels issue is much less clear here about whether fuels you can mitigate the risks as much or at all in some cases. Quickly, before I stop, I wanted to show you just a brief of this recent study that my colleague Keith Lombardo, who's now Chief of Natural Resources at Cabrillo National Monument in San Diego, he's coming up today to join the class and tell more about this story, working with these amazing bigcone Douglas-fir. So these are these Douglas-fir trees that live in the sea of chaparral, right here in your forests. These are amazing trees. They're the most fire-adapted conifer I have ever seen. And this is the Zaca fire with totally nuked landscape, and then look, those are bigcone Douglas-fir. So these guys get burned up. They burns up the canopy. You can have total canopy kill of these trees, and they just resprout. They just resprout little branchlets from the stems, and they do this repeatedly. That's amazing. They have really thick bark. These guys are survivors. Extreme survivors. They have to be. These are conifers living in a sea of chaparral. So Keith and my colleague Chris Basin, these guys did some pretty serious surgery, biopsy surgery of plunge cuts with chainsaws. We didn't hurt the trees too bad. Small wedge sections on the uphill side, and about 8 out of 10 trees have fire scars in them and other indicators. So we see these wounds anywhere from 1 to 4 or 5 lesions that are fire related. And we are able to match these very well with fire atlases to the 20th century. So they're corroborated by fire atlas. We also see changes in growth, surges, and suppressions in growth. So Keith has been able to compile this amazing fire histories. One study published here in Los Padres, and then 2 more to come with a couple of other papers from his dissertation, which is completed. And this is in Los Padres. So these individual lines here are the fire histories from stands with multiple trees sampled, and the tick marks are the fire dates. The black tick marks are the fire dates from different stands in the Los Padres. The blue lines connecting some of those are the less widespread events, like 10% or fewer of the stands recording a fire, and the red ones are the fire dates that are synchronous over 25% or more of the stands in this part of the Los Padres. So, is there a change in the 20th century? Maybe. Well, if you just looked at the red ones, actually no, there's no statistical change in the intervals between widespread fires. Widespread fires burn every 30, 50, 60 years in chaparral, and they have for hundreds and hundreds of years. However, there are actually more small events that tend to be less synchronous before 1900. So Rich Minnick and John Keeley have both seen this graph, and both of them kind of like it. For those of you who know the debate about this. I think actually the other sites that Keith has in the Los Angeles and San Bernardino it doesn't show such a clear, one of them shows this kind of thing in the 20th century and the other one doesn't. So maybe the jury's out whether or not really there's been a decrease in the number of smaller events. You might expect there might be with fire suppression, there'll be fewer small events. But has that had an effect on fuels or in fire occurrence and severity and size? I don't know. Last couple of things. This is a little more on the apocalyptic side. And again, the whirlwinds. This is a phenomenon. They occur at different scales. There was actually an event here in the Los Padres that resulted in injuries to some firefighters. Check this out on YouTube. It's actually a lessons learned YouTube that shows, there's some video of the footage and tells what happened. Firefighters need to be cognizant of this. And then on a sadder note, of course, this last summer in Arizona, we lost 19 firefighters. There they are. This is like hours before these young men died. In that type, that's chaparral. Actually, this is Prescott, Arizona, dead. This is drought-killed chaparral, okay? A really, really sad event. Interesting, this landscape was more forested back in the 19th century. It was very heavily logged. It's the most intensive mining area of Arizona. And so a lot of this area was formerly forested, converted to chaparral because of human actions. And next to last, I think, is, this is where we really do need to take this seriously. This is not just about firefighters, it's not just about watersheds, it's about people. There people are being killed. In Australia, in 2009, over 170 people were killed, 400 injured in 2009. Tasmania had an incredible firestorm. Check this out on The Guardian. This is an awesome multimedia story of the newspaper The Guardian that interviews this family and what happened. They barely survived, and the grandfather was just literally jumped into the lake at the last minute while the grandmother and kids were waiting there. So this is, this is a bit apocalyptic, but changes are coming. What is it going to take for us to respond properly? It's going to take different kinds of actions, different places. Dealing with greenhouse gases is really important. This paper, Park Williams' paper, is looking at the distant into the 30, 40, 50 years from now using downscaled models of warming temperatures, and the picture's not good. One of the punchlines from this study that Park and a group of us just published is that by 2050, the average springtime temperatures, the average drought conditions are equivalent to the drought conditions of the mega droughts of the last 1,000 years, the most extreme mega droughts of the last 1,000 years. The average conditions, as predicted by about a dozen downscaled regional climate change models. Let's hope the models are wrong. I suspect they're not entirely wrong. Let's do something about it. Thank you. A few minutes.
Thank you very much, Dr. Swetnam, for your fascinating talk. You showed a very compelling and concerning graph showing the increase of wind-driven fires, increasing in frequency and length over time.
Right.
And just taking it on face value, you think, wow, that's a little bit scary and we'll have to deal with it. But one thing I was wondering is if you've thought about and reflected on how suppression of fire relates to that graph. And my thought would be wind-driven fires are so dangerous that the firemen are not going to be in there fighting them. They're going to be off to the side. So your graph is probably accurately reflecting a natural process. Do you have any thoughts on how suppression relates to that graph and if you think it influences the frequency?
Yeah. Well, it's a tough one. It's very difficult, impossible, really, to totally parse out how much of the changes that we're seeing are related to changes in fuels versus changes in climate in these types where there's been increases in fuels. So in the Ponderosa pine types to the southwest, where that record is from, there's clearly been increasing fuels and increasing densities of the forests. But it's hard to say what percentage of this change is due to the fuels and how much is due to climate. One clue is that the 1950s actually had as deep a droughts as that we're having now, but they weren't hot droughts. And we had actually the fuels at that time, and many of these forests had high density stands in the 1950s. And yet, the largest wildfire, the largest forest fire in New Mexico and Arizona in forest before 1980 was about 50,000 acres. 50,000 acres. Now we've had 500,000 acres. So based on that, there were what I'm saying is in the 50s, there were fuels were already there. It was a pretty warm drought, but it was a pretty deep drought, but it wasn't a hot drought. Now we've got the fuels plus a hot drought, and the fires are 10 times larger. So, you know, I think the warming temperatures are a key factor. I mean, they may be the primary factor. But again, fuels are contributing. Now, whether or not, I mean, what to do about this in terms of, I mean, firefighters, the unpredictability of it is with the winds, they can come up so fast, and the behaviors, things can switch and change. The example from the Los Padres here, where they were caught, this was a smaller vortex, and this thing changed direction very suddenly. So even though firefighters may think they're out of the way, they may not be out of the way. And if you look at what happened in Australia, this was warning time, you know, high winds, again, high winds, where people at night, and people didn't get the message, or they were doing some other kind of thing, were waiting, and then when it came, it was too late. So it's the speed and the behaviors, the unpredictable behaviors of these things that gives me pause. I mean, I hate to be alarmist, but it's like, I'm actually surprised that Southern California hasn't had a very high fatality event. And, you know, this is what everybody is cognizant of this, I hope, but what are we doing about it? What can we do about it? I don't know what the answers are, but it is a real possibility that we're going to be faced with a black swan kind of event where we didn't really anticipate it because it's a behavior we haven't seen before.
So you're emphasizing the human factor in fires. Well, how do you tease out the fact that we have more people living in the wild and urban interface than ever before? And so now we have so many more ignitions than in the past.
Yes. Yeah, I mean, this is the Southern California case is that for sure. You see that as populations have increased, the number of ignitions have greatly. Was that me? So your question about was.
So you're saying we're getting bigger fires, we're getting more frequent fires.
Yep.
That might be just more people lighting fires.
Yeah, no, actually, I think we're basically at the saturation point of ignitions. And that's true, I think, in Southern California. There's so many people on the landscape that when the conditions become ripe for fire, like it's really dry and it's windy, you're almost guaranteed an ignition. I mean, just an example, this is the way it is in the Southwest, too, where we have lightning, right? And there's so much lightning that the ignition sources are not really limiting. It's really about the fuels. We had a big fire outbreak in 2011 in Arizona. It was really windy and really dry, and they were down fighting one of the big fires south of Tucson. And during the day, the first day of that fire, the firefighters started 6 separate fires by accident, just by parking their vehicles off the road in the grass, by a bulldozer pushing rocks and causing a spark. I mean, the point is that when the fuels are ready and the winds are there, you know, they're going to burn. And when you've got a landscape like Southern California with thousands and millions of people actually traveling around in the hinterlands and burning stuff in their backyard, you know, it's really not the ignitions are really not a limiting factor.
It strikes me that most of the southwestern ecosystems that you've studied are pretty low diversity in terms of the conifer component.
Mm-hmm.
And so it seems like those are the areas that are going to be most susceptible to actual complete loss of the tree canopy over time. And I'm wondering if you've tried to sort of map out the extent to which there will actually be whole-scale vegetation conversion from what used to be conifer forest to something else.
No, this is a really, you know, a big question is where is the type conversion going to occur? What is the patch size? What is the patch size that will limit ponderosa pine from regenerating into forests? This is a really critical question now because there's a debate in the ecological community about, well, there were crown fires in ponderosa pine, especially you go farther north. There were some stand replacing fires in ponderosa, and they're patches, but how big were those patches, right? It's a very heavy seed. So dispersal is, at some point it becomes totally, you know, bird dispersed. It cannot disperse by wind. Plus, if it goes into shrub and grass, you may not get, and then it burns every 20 or 30 or 40 years, it's just not going to come back to forest. So I don't have actually I don't have that answer. What is the patch size that is not sustainable in ponderosa pine? I actually think it's on the order of 1,000 to 1,000 acres and up. Below that, you may be able to seed it in time. But we're getting many events now with greater than 1,000, up to 10,000 acre canopy holes.
Tom, for a great talk, and Tom will be around for another 10 days.
My pleasure.